Thank you very much. Let me start by thanking the organizers of this conference. Although I'm sitting in Uppsala, welcome. I miss being in Korea. Uh, could you just confirm that you can see my slides, please?
Yes.
Okay, great. So this is the outline for my presentation. I will give you some background on how the package came around, and then I will go through sort of the history. And I think it's important to put you in the context of what I said in the title, 50 Shades of Fortran. And then I will discuss the developments we've been doing in the project for the last 10 years. And at the very end, I will invite you to a discussion where I will present my opinions of what I think one has to do with these legacy codes. So the background is I'm sitting in Uppsala, and in Uppsala we had Roland Lindh starting up as a professor in quantum chemistry some 60 years ago. He was officially by royal decree made a professor in quantum chemistry. In Stockholm at the Institute of Theoretical Physics, Inga Fischer-Hjalmars was sitting. Here's a nice picture. You see Inga here and Per-Olof. This is out at the Sunniball Island, 1962. And to much of us Swedes, and maybe also internationally, they are the parents of theoretical chemists, and some people even internationally say that Per-Olof Lindh is the father of quantum chemistry. Inga was more towards getting results and using computers. And one of her PhD students was Björn Roos. Here's a picture of Björn in front of the best computer sometime early in the 1960s. Björn did semi-empirical methods, and that was the content of his thesis. And after completing his thesis, he went to do a postdoc at IBM, where he joined the group of Enrico Clementi. And Björn have told me that one of the most important things he brought back to Sweden was the IBMOL package, or IBMOL package, which is essentially a SCF code. He was very intrigued by this and what is learned in the United States. And he formed his own research group at the University of Stockholm. And his first three students were Jan Anlöv, which most of you know through the molecule code, but you also probably know him through the direct SCF procedure and other things that he's been instrumental in developing. He also had Per Sigborn there as one of his students, and Björn and Per looked a lot on the dynamical correlation problem, and Per developed the MRCI methods. Actually, this is a module that is still around in the OpenMolcas package. There was a third student, Ulf Wahlgren, and he was mainly interested in relativity. And then, of course, Björn, he was the driving force for multi-configuration methods. And I think you already here sort of can see the framework of what eventually became the Molcas project. Here, by the way, is a nice picture of the four of them. I never had a chance to work with Björn's three first PhD students. When I got into the picture, the last one just had disappeared out a few months before. Here, for instance, is something I have in my possession. This is a manual, an original manual to the molecule program. This was the program that inspired me to write Fortran codes and to myself become a developer of an integral code. Anyhow, in 1989, Björn got an award with money from banks in Sweden to develop a project in which these codes, molecule, the COSSF code, and the MRCI code were joined together. And he did this together with the authors and other developers in Sweden. The packages this time was mainly written in Fortran 4, Fortran 66, and some was written in Fortran 77. And for the first 20 years, the Molcas project was a very much centralized Lund project in which Björn decided almost everything. Also, during this time when it was a Lund project, it was a commercial project, and we went from release 1 that was in the, I don't remember if it was 1989 or 1990, to the last release as a commercial package, which was in 2009. Because of health issues, Björn stepped down from the project in 2009. And since that, I have been involved in trying to lead this project. During this time, the Lund era, a number of important projects were developed. I'm just mentioning 2 here, the RASI code and the COSPT2 codes. The COSPT2 code here is the canonical COSPT2 code. Here's some pictures of some collaborators from that time. I think you're familiar with the faces: Jeppe Olsson, Per-Åke Malmqvist, Valera Vuriasov, Per-Olof Widmark, Francesco Aquilante, or Thomas Bonde Pedersen. The package was developed by people that really didn't know how to develop a software project, neither how to maintain it. And at some point, it was obvious that we had to do something about it, and that we had to start to use modern development philosophy and platform for this. And this was something that came to us about towards the end of the 1990s. We did that in-house for a long time, but when I took over, I realized that the future of the project cannot depend on Lund University and the research group there. That would be just too narrow. So I would like to open the project to more developers, and I did so by starting the developers workshop and making the project an international project. The workshops would be a place to get people to be motivated to join the project. It would be a place to discuss the future strategies to use in the project. It will also be a place where people can present implementations. Normally, when we go to international conferences, people are not very interested in hardcore computer implementations. So I saw a need for that. Also at these workshops, we invited people from outside the field or our groups to give us new scientific perspectives and to find computational challenges. But also it was the place where we made the key decisions on what to do. We have had 8 workshops so far, and we're going to have the 9th one over in the UK next year. This has been very helpful, and as you can see, we've been in the Middle East, we've been in the United States, and we've been in Europe. So the important thing I think with what we did was that this shoemaker stay at your last is that we should concentrate on the things that we are good at. And that's the developing quantum mechanical, quantum chemical methods. We should not waste time and resources on version control, compilation and installation procedure, error control, how to maintain and develop software for writing manuals and document, or writing software for memory management, or the whole apparatus around code verification. Unfortunately, this is something we did in the past, but now we have to let go of that. So the important things was that we was tapping into the enormous resources there is in the community with respect, for instance, to continuous integration. We had our own version control package that we used to maintain the package. We let go of that and moved everything over to the Git repository. Also, we started to realize that we need to get the code as clean as possible because we want to have it on as many platforms as possible. So during the years, we have now a code that more or less compiles without any compiler warnings. We're removing old structures and old approaches. Before, we had developed our own script to install and compile the code. Nowadays, we're using the CMake resources. And we also recently, a few years ago, decided that this has to be an open source project under the LUPL license. And all development will be public. And we will open up for external mergers. The package nowadays support all modern Fortran dialects, and we're trying to move away from old formats, like we recently introduced the use of the HDF5 format in the package, and also we open up a community platform for developers to communicate with each other. Let me just briefly give you a chronology of what happened with the package the last 10 years. So here on my left side, I have the commercial branch of the package. And here you can see the release versions and which year this happened. And about here, 2013, we had the first developers workshop. A few years later, we determined that we should go towards an open source platform. And for a short while, the OpenMolcas and the Molcas package were like two conjoined twins. They were integrally integrated into each other. But sometime around 2016, we opened up the Git repository for the common code here. In 2018, we made the Git repository public, and at which time the commercial side was let aside. And as a consequence of that, I stepped down from the commercial part of this project. The commercial part now is essentially a polished up version of OpenMolcas, and I don't have anything at all to do with that anymore. So where do we go, and how do I see on the developments that has to be done? So during my career, I have seen a lot of what people say top-notch languages. When I started off as a student, it was COBOL, later Pascal. At some point, everybody said that the thing you have to do is C, Java, C++, and now very recently, everybody says you have to do it in Python. Well, I learned Pascal once, I forgot it. I learned C once, I forgot it. I tried to learn Python, and I have forgot it. There is an alternative way of doing it. It's this. It's consistent, and it builds on top of what was before. Fortran can also be propped up to use different versions of accelerators, so you can still use the very same code you had. You don't have to write something new. And I would quote Charles Darwin as saying that it's not the strongest of the species that survives, nor the most intelligent that survives. It is the one that is the most adaptable to change. And I would argue that Fortran is that language. Also, I'm sort of asking for the wisdom of wasting away 30 years of program and software development. I'm asking myself if the current hardware standard as we use today is the one that's going to exist in the future. Am I, by adapting too hard to a particular hardware architecture, putting me in a situation in which all that code is going to be completely obsolete 5 times later, and I have to redo the whole effort again? Should I take the risk and rewrite everything to Python or to C++ just to discover that that language now suddenly has become obsolete because somebody has figured out an even smarter, more flexible language? And also, I challenge you and I say that I'm asking the question, is it hardware or software development that will advance our field? Well, looking at the enormous development of computer hardware and speed, and you actually compare that to the method developments the quantum chemists have done, it actually turns out that if I was a quantum chemist and I had to choose between a 10 years old computer with the methods of today, or if I would prefer to have the computer of today with the methods of 10 years ago, it's obvious I would choose the old computer. We have advanced the field much more than the technology has advanced it. So I don't think we should sort of adhere too much to a particular hardware or software solution. That's not where the breakthrough is going to come. So I tell you, I advise you, don't jump on the bandwagon. Be a bit cool about it. When you develop your software, try to develop it such that it's flexible and adaptable. Don't put all the eggs in one basket. And I think the two latter things are pretty obvious statements. And those of us that have these legacy codes, I think we should be a bit cool and try to see how we can adopt to the new technology that comes. I don't think the solution is to scrap the packages we have. I don't think that's smart at all. So when I look into the future, I say that new algorithms will be the long-term game changers. And it's not hardware, and it's not computer languages. The reason we left wave function theory in the early 1990s for DFT was not because the computers were faster. It was because it was a method that made sense. And we should challenge ourselves to try to find that, at least use as much resources on that development that we would spend on trying to adapt our packages to these new languages that comes around or the new hardware that comes around. I think we should look a bit more into machine learning technology. We in my group have recently used it to find new ways to optimize molecular structures. Also, I think that we will have to look for technology that allows us to write computer code in a way that is much faster than today. I think that developing software that sort of bridges the gap between the equation that I write in the paper and the computer code that actually makes the calculation, that gap should not be a PhD student. It should be a piece of software. If I have an idea for a new method, I should be able to realize that within the next few days. In the meanwhile, I think we should modernize, restructure, clean up old code. And while we do that, we should try to do it in such a way that we facilitate flexibility and future adaptation. But then, of course, it is also a matter of how much resources do you have to waste. If you have a lot of money, maybe you're getting it because there's a grant that is associated with a particular supercomputer. Well, go ahead and spend it. But I'm just asking whether or not that particular investment actually is going to survive with time. So with that, I'm pretty much towards the end of my presentation here. Let me wrap up with a few pictures. First of all, I would like to thank all the developers of the OpenMolcas project.